Okay team, this is the last lesson from chapter 5, and after that we're doing one lesson from chapter 9, so the end is in sight. This one's applications from science and statistics, so we're going to look at some bell curves, some science applications, and so kind of just an example on some of the different types that you, or each of the different types of stuff that you're going to see. So one application that we can do is work. Okay, so work is force, the force at x times x, which is distance. This means force times distance, meaning the area under a force versus distance graph is going to be your work. Okay, so if it's not consistent, you need to use an integral to solve. Or if it's something like this, we can do area. Okay, so find the work done on the interval 2, 6. So that's from here to here. So the way that I did this is kind of split it into that rectangle there, and then I split it into kind of sections like that. So the area underneath this guy, so this rectangle here is a base of 4 and a height of 2. So that's a nice easy, we'll call that area 1. Area 2, that's 2 and 1. And then area 3, I'm going to do both of these as area 3 because each of these guys are, so if this is 3, which I'm assuming it is, and this is 5, each of these have a base of 1 and then a height of 1, so 2 of them stuck together, so it's 1/2 times 1 times 1 times 2 because there's 2 of them, so that's not a 2, it's a 1, my bad. Okay, so then the work from 2 to 6 is 11, and we know work is measured in joules. Okay. Another example is if it gives us an equation, we can find the work done in the first 3 meters if the force is given by this equation here. So again, the work is going to be the area under the equation from, if it's first 3 meters, that means we're talking about from 0 to 3. So we add that dx, so it's a proper integral. Okay, so we could do this graph or on our calculators graphically. We could do it just using the function integration. I'm going to do it algebraically for the practice. This one we've got something under a root, and the derivative of this something is going to be something to do with this. So I'm going to do a substitution. So I'm going to say u is equal to 9 minus x squared. Then du is equal to negative 2x dx, right? Because it's normally up there, or down there, we move it over. Okay, so then because we don't have a negative 2, we need to divide both sides by negative 2. And so this can go in for this x and dx here. So this is going to be the integral when x is equal to 0 to 3. Remember, we can't plug these guys in for u because our variable has changed. So it's going to be root u times du over negative 2. So that negative 1/2 can come out in front. And then the integral of this is, I guess we could write this as u to the 1/2. So the antiderivative is going to be to the 3/2 because we're adding 1 to the exponent. And then to give us a 1 out in front there, then there must have been a 2/3 in front that when the 3/2 came down, it multiplied and turned it into a 1. And so that is going to be evaluated from x equals 0 to x equals 3. Now, we can either plug the x's back in, or we can figure out what u is at those points. Okay, so this is going to be 1/2 of 2/3. I'm going to put x back in, so it's going to be 9 minus x squared. We're plugging a 3 squared, and then 2/3, 9 minus 0 squared. Oh, Oh, and then these guys are to the 3 halves. I knew I was forgetting something. 3 halves. So we've got 9 minus 9 is 0, so that's nice. We can do the 0 to the exponent of 3 over 2 is still 0, so this whole thing is 0, so it's 1 half of 0 minus 9 to the 3 halves. So think about if we rewrote this as 9, this is 9 square rooted cubed, right? So we can either do the square root first and get 3 and then cube it, so we have 27. That seems easier than trying to do 9 cubed because I don't know what that is. Okay, so this is 27, but we've got 2/3 of 27. Okay, so the 2's are going to cancel, and so then we've got 27 divided by 3. Oh, I dropped the negative out in front here. Sorry, guys. So then we have a negative, so that turns it into a positive. 27 divided by 3 is 9 joules. Okay, so we could also do that graphing it. So y1 is equal to x times root 9 minus x squared, and then go second calc 7 for the integration function, and you should get the same thing. That's always a good way to check your answer. On a test or a quiz, I'll specify whether I want you to do it algebraically or if I want you to do it, or if you can do it on your calculators. Another application is a leaky container. On this one, write small. I should have given us more room, but I didn't. So a bag weighs 8 pounds empty, and it's filled with 144 pounds of sand. It's lifted at a constant rate using a rope that weighs 5 pounds. The sand leaks out at a constant rate such that at 18 feet, half of the sand has leaked out. How much work has been done to lift the height of the 18 feet, or lift the height of 18 feet? So how much work has been done for lifting the bag, the sand, and the rope? Okay. Remember that if a value is changing, so if something's getting lighter and lighter and lighter because the sand is leaking out, we don't need a constant force to lift it. So the force is going to be decreasing for the bag. Okay, so if we think about this, I kind of envision it on a pulley with the rope, kind of like that. So here's it at 0, and at 0 we've got 144 pounds of sand. Okay, and then at 18 feet, half of that sand is gone. Okay, and this rope itself weighs 5 pounds, so we need to consider the fact that as we pull it up, it's going to be decreasing the amount of weight that we have to lift. Okay, so the first thing that I'm going to do is I'm going to do the bag. So again, write small. The bag is a constant force, right? Because the bag is going to weigh that 8 pounds no matter what. So work is equal to force times distance. So pounds is a force, just like newtons. So it's going to be 8 pounds times, how high does it go? 18 feet. So this is going to be 144 pounds. Okay, and that's how we write it. It's like the imperial version of a newton. Okay, so that's part of my answer. That's how much work I did to lift the bag 18 feet. The rope is also going to be, is going to be a decreasing force. Because as we start lifting that rope, then we actually, or as we start like pulling it down, we actually have to lift less and less, or pull on less and less of it. Okay, so the work is going to be the integral of force times distance again. So we have to come up with an expression here. So the force where is constant rope? So the force is going to be a constant force, or sorry, a changing force that starts at 5. So the force is going to start at 5, and then it's going to decrease based on the amount of distance. So 18 minus x. Okay, so originally you're lifting all 18 feet of the rope, and that's the 5 pounds, and then you're starting to subtract that. Okay, so then distance is going to decrease, and that's going to multiply in with your force. And then dx. And so we're lifting that from 0 to 18. So then if we distribute, this is 90 from 0 to 18 minus 5x dx. So then when we do the integral, it's going to be 90x minus 5x squared over 2 from 0 to 18. So if we plug everything in there, then that's going to be 110 foot-pounds of work done for the rope. Okay. Then we need to think about the sand. So the sand is the most complicated bit. So it is decreasing. So the sand is actually physically leaking out. So if we drew a force versus distance graph, it's going to start with 144 pounds of force, and it's just going to slowly leak out until all that sand is gone. Now it says that so let's assume that here is 18 feet. That's where half of the sand has leaked out. So that would mean 72 pounds of sand are left. So that would give us 36. By the time we lifted 36 feet, the sand would be gone completely. Okay, so we need to come up with some sort of equation to figure out what this graph is, so that we can integrate this area under the graph from 0 to 18. Okay, so I'm going to say my b value is 144. My slope, if I do y1 minus y, or y2 minus y1 over x2 minus x1, I get -4. And so then my y is -4x plus 144. So that's what I'm integrating from 0 to 18. So -4x plus 144 dx. So this is going to be, it's going to start with a 2, so it should have been an x, or it would have started as an x squared. A 2 would have come down in front and multiplied. So this must have been a -2x. And then the integral of 144 is 144x. Done from 0 to 18. So when I plug that in, I get 1,944 foot-pounds of work. Okay, so then a total would be, I don't actually have that calculated. I guess it asks us as individuals. So we don't need a total because we answered to do the bag. There's the force, or the work done to lift the bag. There's the force to lift the rope, and there's the force to lift the sand. Okay, or sorry, the work to lift all of those. Okay, so we did all of them as separate bits. Another application, so another leaky container. A water barrel containing 200 gallons of water is punctured and begins to leak out at a rate of 15 sine pi over t, or pi t over 30 gallons per minute, where t is measured in minutes on the interval 0 to 15. Okay, so this, if we know, like if we picture this graph, this is the rate that it's leaking out. So this is going to be sinusoidal. Maybe it's, I don't know, on a truck or something, and it's sloshing around and it's leaking more when it's on a certain side, something like that. But that's how it's leaking. Okay, so how much water is leaked out after 7 minutes? If this is the rate, okay, so this graph would look like amplitude at 15. So let's just graph it. Let's give ourselves a visual. 15 sine of pi x over 30. That already was zoom trigged. Zoom standard. So we're gonna have to zoom out because if my amplitude is 15, I definitely need a bigger window. So let's go y max to 30, 30 and x max to 50 and see what happens. So here's my graph. So this is probably actually, it's leaking slowly until it reaches a maximum leakage. So maybe the hole gets bigger, but then there's less pressure on top of it, so it starts to slow down. Okay, so that could be a way that we describe that. Okay, so my graph looks like that. And so if I want to know how much water is leaked out after 7 minutes, I'm going to add up the first 7 minutes of area under that graph. So it's going to go from 0 to 7, the integral of this guy. So when I integrate, that 15 can come out in front. The integral of sine is negative cos. And remember that this would have been multiplied, if we did the derivative, we would have to multiply by pi over 15, which means there must have been a 15 over pi out in front to cancel that. Or sorry, not pi over 15. I changed it to a 15. These are 30s. Oop. Oop. And we're going to evaluate that from 0 to 7. So when I do that, I get 36.79 gallons. If we want to write an expression to represent the total amount of water at any time, we know that the volume left in the tank is going to be from the 200 that started minus whatever is leaked at that given time. So it's going to be 15, the integral from 0 to whatever time we're talking about of 15 sine of pi t over 30 dt. At what time to the nearest minute will there be half of the water left? Okay, so then we want to say, okay, well then that is going to be 100, the volume of 100. Oops, should be minus. And so then we can just actually solve using this integral. Okay, so if I move the 200 over, then I have negative 100 over here. And then that 15 can come out. It's still a negative because of this guy. And then we're doing, I'm going to move this down a little bit so I have a little bit more room. So negative 100 equals negative 15 because that 15 is going to come out. And then we're doing the integral of this thing. So again, it is negative cos of pi t over 30 times 30 over pi from 0 to t. So we can plug that in even when we have variables. So I'm going to divide both sides by 15 before I do that. So 100 divided by 15, I can divide both of those by 5. So I'm going to leave it as 20 over 3. Negative divided by negative makes a positive. And then we have negative cos of pi, this t's going in for there, so pi t over 30 times 30 over pi minus negative, so this is going to turn into a plus, cos of pi t over 30, or pi times 0 over 30 times 30 over pi. So this time we're plugging the 0 in for the t. Okay, so now we've got this whole thing turns into a cos of 0. So we've got 20 over 3 equals, or let's not do it as 20 over 3. I'm gonna multiply both, or divide both of these sides by 30 over pi. So if I do that, I'm going to get rid of the 30 over pi from both terms here, and then divide this one by 30 over pi, and then I'm going to turn it into a decimal. So it's going to be 0.69813. Okay, because this is already saying to the nearest minute, we can round it. Okay, so that's going to be negative cos of pi t over 30 minus negative cos, so plus cos of 0. Cos of 0 is 1. Okay, so if we subtract 1 from both sides, we get negative 0.301868. So then we can get rid of the negatives. Then you're doing cos inverse of this guy gives you this. So then, well, this is pi t. So then pi t over 30 is equal to cos inverse of this. So if you do that on your calculator, you get 1.26414. Oops, I was not looking. So then t is equal, if you multiply by 30, divide by pi, 12.07 minutes. Okay. So there is where half the water is left. Because remember, it's not just going to be at the midpoint, so 7.5, because water is leaking slower. This is a rate, not how much water is left, right? This isn't a graph of the water. This is how quickly the water is leaving. Okay, one more, or a couple more. So if we have fluid force and fluid pressure, pressure is equal to W times H, where W is weight density, so each different liquid that we might interact with would have a different weight density, so like water or olive oil or whatever, and it'll always be given. Water has a weight density of 62.4 libs per foot cubed. Okay, so if there's ever any questions with water, this is the number that you're using. Okay, so a fish tank with a base of 2 feet by 4 feet. So I'm going to draw this for us. So there's my base, 4 feet by 2 feet. And a height of 2 feet. So there's my height of 2 feet, is filled to within 2 inches of the top. So we have the water line kind of going along there. What is the fluid force against each vertical end and horizontal end of the tank? Okay, so we're just going to do these ends of the tank. Okay, so we're just going to do each, like, this question is worded funny and I always forget it until I see it again. So we're just going to do against this side of the tank. Okay, so against this side. Okay, so we need to figure out if we want force. Force is going to be a function of pressure on an area. So if you think about, like, I don't know, the glass aquarium or something, like if this was an aquarium and you were walking underneath it, you would want to know that this glass is strong enough to withstand the force that the weight of this water, which is going to be based on its density over how much area it's distributed over, is going to be okay. Okay, so force is always going to be the integral of pressure times area. So this is like a newer, we didn't talk about this in Physics 20, but this is something that I will give to you if you ever need it. So force is the integral of pressure times area. Okay, so we need to figure out what the pressure of this water on this side of the glass is, and then we need to figure out what the area of that glass, or of the glass in question is. Okay, so I'm going to move this from my diagram so we can draw something else. So this tank is 2 feet tall, but it's not actually all the way up there. So I'm going to name that Y. Okay, we're going to do this integral as far as adding like horizontal chunks together. So we're going to do it in terms of Y instead of X, because as like each layer of water sits on top of each other, like if you picture like layer 1, layer 2, layer 3 of all the water, it's going to become more pressurized, right? The more water is sitting on top of you, the more pressure you feel, which is why at the bottom of the pool sometimes your ears hurt or whatever. Okay, so we're going to do it in little horizontal planes on this glass. Okay, so the area of this glass is going to be 2 times, we're going to call it delta Y. So we're going to start from the base, and as we add water, we're adding that Y dimension. So we're going to call it the change in Y. In calculus, we talk about the change in Y as adding those little tiny bits of dy. So we're going to do 2 dy. The pressure, so that's that formula up here, is W times H. So W is 62.4 if it's water, and then H, how high it is my Y value. Okay? So there is my area and my pressure. So now I'm going to do the integral of that. So my pressure is 62.4 Y. My area is 2 dy. Okay, and then we have to figure out what are boundaries. How are we going to? What are we going to stop adding this up? So we're going to start at a height of 0, and then we're going to stop when the height is. It said that it's filled within 2 inches of the top. So it's going to be. If we think about 2 feet is 24 inches, this is 4 inches short of the top. Okay, so we're going to do 20. It's not 4 inches short of the top, it's 2 inches short of the top. I don't know where I got 4 from. So it's going to be 22 inches. So 22 inches, but we need to convert that to feet, so we have to divide it by 12. Okay, so there's our boundary. So, because these things are measured in feet, not inches. We could have done it all in inches, but we did feet. This is in feet, and this one will be a really hard one to change, so it's easier to change that one. So then the integral of this is going to be, so the 64 or 62.4 times 2 can come out. I'm going to leave it like that, and you'll see why in a second. And then we do the actual integral. So we're doing the integral of y dy. So what's the antiderivative of y? That's 1/2 y squared. That's why I left it like that, because the 2's are going to cancel. So we have y squared times 62.4 from 0 to 22 over 12. So then that's going to equal, when we plug those in, This is just going to be a minus 0 term, so it's going to be this squared times 64 or 62.4, so 209.73 pounds of force on that glass. Okay, so you'd want to make sure that that glass is sturdy enough for that to be okay. Okay, this next one, this application of work done pumping, we're going to skip that for this year, so don't worry about that one. And then our last application is probability. So hopefully you guys are familiar with the bell curve. I know I talked about them at some point in Math 30 about how the provincial average, they want it to be a 65, and then using a normal distribution from there. But probably that didn't mean a ton. So here's some stats and probability application. If you guys take stats in university, you will see lots of this. We, as far as probability, what you guys need to understand for now, it's measured from a value from 0 to 1 or as a percentage from 0 to 100. So 0.76 would be 76%. When we talk about average, it is denoted by this mu or an x. Okay, so that's our like x coordinate. Our normal distribution is data spread evenly above and below the mean. Okay, so again, here's my mean, and then we're normally distributed on either side. Okay, so again, on this axis. And then standard deviation is how spread apart a set of data is from the mean. So noted by, I think this is lowercase sigma or the letter s. Okay, so if you've got a really tall bell curve, that means your standard deviation are small. And then if you've got like a really flat bell curve, that means your standard deviations are big. Okay, so this is kind of the normal distribution curve. So what this is going to mean is, here's my mean. Okay, so my mean is always going to be 50% of the population. So 50% are going to be below it and 50% are going to be above it. In Alberta on diplomas, they want a 65 average, where 50% of the population is above that average and 50% is below it. Now, 68% of that population, so here, is going to be within, so 68% within one standard deviation. So whatever they decide one standard deviation is going to be, 68% of the population is within that. Or that's how you can figure out what that standard deviation is figuring out 68% of this area is this far apart. Okay, then 95% of the population is going to exist within 2 standard deviations. So from the normal, 2 standard deviations. I drew that weirdly. 2 standard deviations over. That's 99 or 95% of the population. So then this is 5%, kind of on the outliers. If you did a 3rd standard deviation, 99.7% are going to be within 3 standard deviations. So 0.3% of the population would be outside of 3 standard deviations. Okay. So that's the normal distribution curve. So these numbers are numbers that stick. So if it ever is talking about like 68%, 95%, or 99.7, you know that that's 1, 2, or 3 standard deviations from the mean, kind of to match those. Okay, so example, the grades of first year university calculus class are normally distributed. They follow a bell curve. The mean scores is 70% with a standard deviation of 4.5%. So we're going to sketch the curve to illustrate that. Okay, so I like to draw kind of like that. And we want it to be as symmetrical as we can get it. It's not quite whatever. Okay, so this is 70% here. And then it tells us that the standard deviation is 4.5. So that would mean 74.5%. And then if you subtract that, so 65.5%, that means, that's a little far down, but this section here would be 68% of the population. Okay, so that's what it means for those standard deviations to be what they are. Then if we added another 4.5, we'd have 79%. If we subtracted another 4.5, we'd have 61%. So then 95% of the population would be in between 61 and 79. Okay, so that's how a normal curve would look like that. So that means only 5% of people got above a 79 or below a 61. So no one got really awful marks, no one got really great marks. Everyone was kind of just in the middle here, or 95% of the population was. So yeah, if, as I said above, if you have a smaller standard deviation, you have a higher bell, because for 68% to fall within it, if you have this tightened, then it's going to have to be taller. And then a larger standard deviation, you're going to have a shorter bell. Okay, so the normal probability density function, so how many is under each point on the x-axis, and we call this a Gaussian curve. You don't need to know too much about that. For a population is this function. So it's 1 over, this is our standard deviation, the root of 2 pi, e, so that's Euler's number, x minus u squared divided by 2 standard deviation squared. So x is going to be our variable, right? So that's how far along this we are on the x-axis. So that's our unknown. And mu is our mean, or our average. Okay, so we've got standard deviation, we've got our mean, and then x is how far across we are on the bottom there. Okay, so that's how we can figure out this, and that's what we're going to actually be integrating. Don't worry, our calculator is going to do this one. So the mean height of an adult female is estimated to be 63.4 inches with a standard deviation of 3.2 inches. So what's the probability that an adult female is less than 63.4 inches tall? Okay, so the first thing that I'm going to do is I'm going to draw a bell curve. Okay, I'm going to get symmetrical as I can. So this would be 63.4 inches. And then if it says 30 or 3.2 is my standard deviation, if I add 3.2 and subtract 3.2, I'm going to get 66.6 and then 60.2. Okay, so 68% of the population lays between those two heights for females. So what's the probability that an adult female is less than 63.4 inches tall? Because that's the mean, if this is normally distributed, and we're assuming it is, then 50% are below that. So this is just going to be 50%. Okay, so it's half of the bell curve. So we don't need to be able to calculate an integral to know that. We just need to understand what a normal distribution is. Okay, if it's between 63 and 65 inches tall, we want to know between like here and here. But there's nothing standard about our probability. There's no standard deviation, anything like that we can be like, okay, I'll just plug in. There's nothing we can do. So this is where we need to do calculus. So we're going to do the integral, the area under this curve between 63 and 65. And this is where that formula from the sheet previous comes into play. So it's 1 over, the standard deviation is 3.2, times the root of 2 pi, and then times e to the negative bracket, x, so that's our unknown, so that's what we're integrating in terms of, minus the mean. Okay, so this one is mu, and this one is sigma, so 63.4 divided by 2 times 3.2 squared. And make sure you're dividing by all of that. That's why I put that extra set of brackets in, dx. Okay, so you're just going to punch that into your calculator. Make sure you're using appropriate brackets and all that. Okay, I get 0.241. So that would mean 24.1% statistically of the adult female population are between 63 and 65 inches tall. 60 inches is 5 feet. So between 5'3" and 5'5" would be that measurement. That makes sense that about 24% of the population is, that's a good chunk, okay? Taller than 6 feet. There's not a ton of ladies. If this was men, we'd get a much higher number, but there's probably not going to be a ton. Okay, so 6 feet is 72 inches. Now the problem is I don't know the record for the tallest lady ever, but I do know that people can't be less than 0 inches tall. So what I'm going to do is if I look at my bell curve, the people who are taller than 6 feet are over here. But again, I don't know where this thing actually zeroes out. Okay, so I do know that it's going to zero out over here at 0. So if I do this whole one, all of the area beneath this, 1 minus the integral from 0 to, this is 72 over here. So 1 minus the integral from 0 to 72, then I'm getting rid of all of this area and I'm left with what's over here because I don't know that end deadline. I didn't actually write the integral. So it's 1 over 3.2 times the root of 2 pi. It's that same thing. So e to the 3.4 divided by 2 times 3.2 squared dx. So I get 1 minus 0.9964. So then I get 0.0036. So that means 0.36%, so not even 1% of females statistically are over 6 feet tall. Okay, we probably know a couple. If you watch professional basketball, you probably know more. But like it's a very small portion of the population, which makes sense. I think I know one woman in my life, not on TV, who is actually taller than 6 feet. Okay. If we're talking about exactly 5 feet tall, then we would be, 5 feet is 60 inches. We do the integral from 60 to 60 of the function. I'm not going to write it out. We know that if we actually don't move over any area, this is just 0. Okay, so this is, I can't spell 0. 0, assuming normal distribution which is kind of counterintuitive because we know in real life we probably know people who are exactly 5 feet tall. The kicker is that from 60 to 60 that leaves no area of wiggle room. So there's a lot of people who'd be like, I'm 5 feet, and it's like really they're 4'9" and 7/8 or 4'9" and 99 out of 100th. Right, like, so exactly 5 feet, you're adding up no actual area. You're taking like that segment and it just narrows in on itself. Okay, if you said from like, let's say 60.1 to 50 or 59.9 to 60.1, then you'd get an actual chunk of that population, which would be more accurate. We probably know people who live within that or even are exactly this, but based on integration and actual probability, mathematically that number is 0, even though we know that that's probably not true. Okay, so here's the things that I want you to practice for today. As I said, remember that these odd number questions, if you look at the textbook, you can find the key for it online. Okay, so those are in Google Drive. If you have any questions from today, let me know. We will talk about them on Monday.